I was trying to think of what you call a string of threes. This is our third speaker in a row from the Smithsonian, George Guice. Is a trifecta or a triptych or I don't know. Trifecta is more active, so we'll call it a trifecta. Sure. Has a gambling connotation, and you might win something. so George Guice is here today from the Smithsonian. He's a postdoc there working with Mike Ackerson, and he got his bachelor's from Kiel University. Which is not in Kiel because it's a little tiny town. It's between Manchester and Birmingham, right? Yep. In the northern Midlands. He did a master's at Exeter University at the Camborne School of Mines, where he studied, obviously, mining geology, and then did a PhD at Cardiff University, where he worked with Ian MacDonald. As he told me when we were talking in my office, he got interested in geology kind of from the geography side. He thought geography was interesting, went and started looking at courses and discovered that the geology courses kind of had everything he liked in it, and then he stayed with geology ever since. His research interests are on the start of plate tectonics, and I asked him why that's interesting, and he said, from his mining geology background, because it's important in how we make ore deposits, which is a really good answer. At the Smithsonian, he's interested in the petrogenesis of mafic rocks from the São Francisco craton in Brazil, and also is looking at some mafic and ultramafic rocks in the Appalachians. But today he's going to talk to us about our high field strength element anomalies, a good proxy for Archaean subduction. George?
Thank you very much, Steve. Can everyone hear me? Good. Okay. Well, yeah, thanks again for the introduction. Thank you, everyone, for coming. It's a real pleasure to be here today to speak to you about some of the work that I did during my PhD, as Steve said, at Cardiff University in the UK. So I'll be asking this slightly provocative question, are high field strength element anomalies a good proxy for Archaean subduction? And what I'll do is I'll present a case study on some pretty detailed work that we've done in the Northwest Highlands of Scotland at this place called Benstrome. Nice field photo there for you. The high field strength element anomalies, the high field strength elements I've just detailed here for anyone who's unfamiliar. I should also say before we get going, my background, a lot of it is in the field, doing mapping and structural geology. There's a lot of jargon associated with field geology. I appreciate I might have a wide audience with a broad range of expertise here today. So if I fail to clarify what certain things mean and you're sitting there feeling a little bit baffled, please feel free to just get my attention and I can hopefully explain what I mean as well as possible. So question one, well, what are high field strength element anomalies and why should we be interested in them? Now, if we went to a volcano that is sitting above a subduction zone, and we grabbed a mafic rock that had been erupted from that volcano, what we would expect to see is a quite distinctive trace element geochemistry. And what I mean by that is we would see negative depletion in the high field strength elements I've highlighted here, relative to other trace elements. Now, the way in which we might want to visualize that, identify that, would be on plots such as this one, a trace element plot. What we're dealing with here, on the x-axis is a suite of trace elements ordered according to compatibility, and on the y-axis is a logarithmic scale with our sample divided by the primitive mantle. So, like I say, if in Phanerozoic subduction zones, modern day subduction zones, this is a pretty well constrained signature that we're reasonably happy with. Increasingly though, we have applied this proxy, this signature, to both other rock types and also rocks of other ages. So here's an example of some intrusive ultramafic rocks, rocks with greater magnesium concentrations. And what you can see here is that depletion in tantalum. There's no niobium on this plot. Depletion in tantalum, slightly lesser depletion in zirconium and hafnium, and depletion here in titanium. Similarly, if we take this proxy and apply it to much older rocks, this is an example of, I think these are about 2.7 billion years old, so they're reasonably young in an Archaean context, but still pretty old. And again, what we can see here is negative anomalies in niobium and tantalum, less so in zirconium, hafnium, and titanium. And these authors would interpret this signature as associated with subduction 2.7 billion years ago in the Archaean. So to give you a bit of context for why that might be interesting for us, let's think about Archaean geodynamics. So what did Earth look like during the Archaean eon between 4 billion and 2.5 billion years ago? So we look at the modern day Earth, and we have a plate tectonic geodynamic regime. We can see evidence for that simply by looking at a satellite image such as this one. So we have the continental crust, oceanic crust. You can see a mid-ocean ridge, subduction zone, the west coast of Chile. And probably we can just about make out the Alps, a continent-continent collision over there. But what was going on during the Archaean? Did the Earth look something resembling this with similar processes? Or alternatively, was something else going on? Now, to try and kind of simplify the discussion, the debate about what was going on during the Archaean, we can kind of ask this question. So when and how did plate tectonics begin on Earth? And while it's a little bit of a simplification, we can kind of subdivide the hypotheses into three broad groups. So group one, up here, group of authors would argue that we've had plate tectonics resembling something like we see today since perhaps 3.6 billion years ago or earlier. And what that means for us as geologists, as scientists, is that pretty much all of the rocks that we see preserved on Earth, with one or two exceptions, are the product of plate tectonic processes, were formed on an Earth that had something like we see today. Second group of hypotheses would argue that something fundamental changed between 3.2 and 2.5 billion years ago. These authors would argue that this fundamental change corresponds with the onset of plate tectonics. And this hypothesis, I think, has probably been gaining traction, particularly in the last 5 or 10 years. What people have done is they've looked at several geochemical proxies, geological proxies, whether that be certain ratios between specific elements, whether that be the presence or absence of specific geological phenomenon, or perhaps looking at the metamorphic grade of rocks. And what a number of authors have noticed is that if you look at the temporal evolution of the Earth, something changes in here. And as I say, this inflection, this change, has often been interpreted as the onset of plate tectonics. What you'll notice is this is a pretty large range. 700 million years is quite a long time. So what each of these proxies is telling us is actually a different inflection point, which might be interpreted as the onset for plate tectonics. Alternatively, and this is admittedly a smaller group of researchers, but worth pointing out, people that would argue that everything that we see in the Proterozoic, everything we see in the Archaean does not resemble plate tectonic processes, and that something else was going on during these periods, and that we didn't get plate tectonics going until about 1 billion years ago in the Neoproterozoic. So that gives you some idea of the scale of the discussion and the debate, and I hope now you can see why this question might be an interesting one to ask. So, are these high field strength element anomalies that we might use to interpret subduction, are they a good proxy for rocks of an Archaean age? Note, subduction does not necessarily equal plate tectonics. While I'm not a planetary scientist, I'm told that Venus has recorded evidence for isolated subduction. Venus, to the best of my knowledge, has not got plate tectonics. So clearly, subduction does not necessarily equal plate tectonics, but if we had widespread subduction in a variety of localities across the Archaean Earth with a chemical signature that is very similar to that which we see on Earth today, it would be reasonable circumstantial evidence. So that's the broad context. Does anyone have any questions at this stage? Mm-hmm. Oh, apologies. Yeah, sorry. I should have gone through that. So ultimately, what we're dealing with in a subduction, and there are potentially many causes. Again, this is a topic of debate. The most common and widely accepted hypothesis would be that in the source of these magmas, where we're creating the magmas underneath in the subduction zone, there is a mineral called rutile. Rutile is a titanium oxide, and it also, crucially, likes the other high field strength elements. So if you produce a magma from this region, leave rutile behind in the source, then the magma that is produced from that will be, relatively speaking, depleted in the high field strength elements. Okay? Other potential causes, like I say, but this would be the prevailing view. So that's the idea, yeah, absolutely. Anybody else want a quick question before I move on to the regional questions?
Just the order of the elements at the bottom?
Yeah, so the order on the elements at the bottom are according to compatibility. So the more compatible elements are over on the right-hand side here, and the less compatible elements over on the left-hand side here. Yeah, so this is effectively like, does an element prefer to be in the melt or in the mineral phase during crystallization? Okay, so now what I'll try and do before I move on to the main part of the talk is give you some introduction to the regional geology. So what then is the Lewisian gneiss complex? Well, it's a pretty small fragment of the North Atlantic craton located in the northwest highlands of Scotland up here. And the North Atlantic craton is mainly exposed in Greenland, but we have a small fragment of it in the UK as well. Some ideas recently that this North Atlantic craton correlates with cratons in Scandinavia and also cratons here in North America. So predominantly, it is composed of what we call TTG gneiss. It stands for tonalite, trondhjemite, granodiorite gneiss. These are three rock types. Essentially, we're just talking about intrusive felsic magmatic rocks that have then been metamorphosed and have a gneissosity. So most of this bit of crust is composed of these TTG gneisses, and typically we would subdivide this portion of Archaean crust into three regions. The northern and the southern regions are amphibolite facies, so kind of a medium metamorphic grade. And the central region is higher grade. It's granulite facies. And I'll come on and give you a more detailed description of this in a moment, but it's important to note that this bit of Archaean crust has experienced multiple phases of really quite high-grade metamorphism. And what I'm interested in and what I've spent a lot of time thinking about is the ultramafic and mafic rocks which exist here. They're concentrated in this central region, so this higher grade region, and you can see that I've marked on the location of notable occurrences, which is with these crosses. You can see they're dominantly located here in the northern part of the central region. As with many ultramafic and mafic suites that occur in Archaean cratons, they've been subject to a really wide range of interpretations that have different implications for this Archaean geodynamic story that I mentioned at the start. So just to point out a couple, Tim Johnson and his colleagues suggested that some of these could represent the sag-ducted remnants of greenstone belts. What do I mean by that? Well, what would have been the case is the TTG forms the majority of this, would have been representing the lower crust. Overlying that would have been greenstone belts, which are denser. And if you then partially melt some of your TTGs that form the lower crust, this density contrast may cause some of these greenstone belts or fragments of the greenstone belts to effectively sink into this partially molten TTG. This hypothesis would be more consistent with a geodynamic regime that is not plate tectonics. Something else is going on. On the other end of the spectrum, they've been interpreted as fragments of Archaean oceanic crust, or fragments potentially of ophiolites or an ophiolite, and this would be more consistent with a plate tectonic mode for the Archaean Earth. So that big scale discussion that I outlined at the start is played out on the regional scale here with the interpretation of these different ultramafic and mafic rocks. What I'm going to be talking to you today about is this locality called Ben Strome. It's located up here, and it represents the largest and the best exposed example of one of these ultramafic and mafic complexes in this region. And before I started my PhD back in 2015, it had not yet been mapped. So one of my tasks was to spend many weeks out in the beautiful Scottish Highlands mapping this. So trudging around and trying to get my fingers on all of these contacts and tracing them. As you can see, it's quite tricky mapping. It's complicated. So just to try and talk you through this a little bit, the lighter blue colors that you're looking at in here are mafic rocks, metagabbros, garnet metagabbros, amphibolites, something like this. And the darker purple and blue colors that you're seeing here are ultramafic rocks, really distinctively layered ultramafic rocks. This is the image that I showed at the start of the talk. So pyroxenites and pyridotites. And this complex, as you can see, has had a lot going on. There's a lot going on this map. So first and foremost, we have it cross-cut by some dikes. These are mafic dikes in the green. There is a large-scale shear zone, east-west trending, that kind of cuts this thing in two, and also some later faulting that you can see in here. So we interpret this complex, and some of the others as well, as representing layered intrusions, or this one is a layered intrusion that was emplaced into the TTG and then has been subsequently deformed. So all of this seeming chaos that you can see can actually be explained by multiple phases of deformation. Just to point out one of those potential things, if we look, follow this blue unit round, it forms what looks like a fold. Likewise over here. And if you trace the actual plane west across the map, you can see that the actual plane itself seems to be folded. So multiple phases of deformation and folding leading to this outcrop scale pattern that we're dealing with today. That's our interpretation. Just to run through then quickly this complex metamorphic history that I mentioned. So first and foremost, about 3 billion years ago, we emplaced those TTG gneisses that I mentioned. If you want to believe our hypothesis, then the emplacement of lead intrusions. This was swiftly followed by a granulite facies metamorphic event, which partially melted some of the mafic rocks that are in blue, and also some of these TTG gneisses. Then had a period of amphibolite facies metamorphism, the emplacement of those dikes that I mentioned, and then to top it all off, another period of green schist to amphibolite facies metamorphism. So there's a lot to take in there, but what you can see is that this bit of crust has really had a pretty tough life. It's been through a lot. It's experienced a lot of metamorphism. So before I then get on to the main point of the talk, does anyone have any questions about that regional geology section? Steve?
How stretched are these ultramafic oxides? You describe them as layered bodies, but often in these kind of terrains, they're deformed. In the fabric of the rock?
Not so much, actually, interestingly, no. There is the idea that these would have, if you look at the stratigraphic thickness of these things, they would have originally been significantly thicker than today, but there's no constraints really on the percentage of that. But yeah, you don't see that in the fabrics, interestingly. Anything else? Okay, good. So what I'm going to talk about today, just important to note, is I'm only going to be talking about these ultramafic rocks, so the layered ultramafic rocks. And part of the reason behind that is that, as I mentioned, these mafic rocks in blue have been partially melted, or some of them have been partially melted. So in order to get rid of that particular complication, we're going to focus only on the ultramafic rocks. You can see where we've sampled throughout. The eagle-eyed among you will notice that there are not 35 dots on the map, and that is because often we will sample multiple rocks within one exposure. So I think there's 6 or 7 samples from this exposure, for example. So when we look at the bulk rock geochemistry for these ultramafic rocks, it became clear to us pretty early that you could subdivide them into 3 distinct groups based on their trace element geochemistry. Group 1, the largest in terms of number, 20 of our samples, display really flat rare earth element patterns, reflected here by the cerium-ytterbium ratio. A smaller group, 11 of our 35 samples, show enrichment in these light rare earth elements on the left-hand side of this plot here, so lanthanum to about samarium. Again, you can see that reflected by the cerium-ytterbium ratio. And then a third, the smallest group, only 4 of the 35 samples, show a much broader suite of enrichment for the light and some of the medium rare earth elements. Again, reflected by that cerium-ytterbium ratio. And that is reflected by the trace element plots that I've shown you from earlier. So the group 1 samples show pretty flat patterns. The group 2 samples show negative niobium tantalum anomalies, and the group 3 samples show these negative niobium tantalum, zirconium, hafnium, and titanium anomalies. Note that the actual tantalum-ytterbium ratios in all three of these samples, in all three of these groups, I should say, are pretty similar. And this grey field that I've put on both of these two plots, it reflects the range from the group 1 samples. And what you'll notice is that the high field strength elements are actually the same in all three of these groups. What is different is these elements that sit around. And the elements that sit around the high field strength elements on these plots are these light rare earth elements that you can see over here. They are located in here. So what it seems to us is that you have the high field strength element anomalies where they exist in these group 2 and the group 3 samples. They're associated with enrichment in the light rare earth elements that you can see nicely on these plots. So the question then is, well, what is controlling the bulk rock geochemistry of these samples? What is controlling this light rare earth enrichment that is controlling the high field strength anomalies? We can ask ourselves a series of questions. So first and foremost, well, we're thinking, is this simply a spatial distribution of samples problem? Are we simply looking at samples from one layer, from one part of the complex? And the answer to that question is no. So we can see that all samples from all three groups are distributed throughout the complex. This is shown quite nicely just by these field photographs. I've marked on the locations of some of the samples in here. And you can see the group 1 samples here and here, the group 2 sample that has some light rare earth enrichment located just between them. So the answer to this question was no. The next question that we had was, well, is there some sort of petrographic control here? Are we simply looking at lots of amphibole in one sample, lots of pyroxene in one sample? Is that all this is? Is it a modal mineralogy problem? Or alternatively, are we dealing with just some specific textures in some of these different groups? And the answer to both of those questions actually was no. So the basic mineralogy of these rocks, olivine, both ortho and clinopyroxene, spinel, the pyroxene has largely been amphibolitised, and the olivine has largely been serpentinized. But there is a range of modal mineral abundances in all three groups. So there is some samples of in group 1 that have very little amphibole, some that have a lot of amphibole, some that have little clinopyroxene, some that have a lot of clinopyroxene. The full range is seen in all three of these groups. Similarly, if we take a look at these element maps, one for each of the three groups, you'll notice that the textures that we can see are really similar between the three groups. So the answer initially to that question was no, there doesn't seem to be a petrographic control. However, what we did notice was the presence of carbonate minerals in the group 2 and the group 3 samples. So those samples which have the light rare earth enrichment, these high field strength element anomalies, these samples and these samples alone display carbonate minerals. They exist in a variety of morphologies. So you can see here top left, they form these veins. Here in top right, they're forming sort of veins within amphibole. Bottom left, they're sort of grains within amphibole. And bottom right, these are forming kind of clots within a serpentinite. So we can cross petrography out kind of 2/3 of the way, but leave some of it uncrossed because we've seen these carbonate minerals within the group 2 and the group 3 samples. The next question that we had was, well, is this a mineral chemical control? Are we simply dealing with differences in the composition of specific minerals? And if we take a look at orthopyroxene, there is very limited difference between the group 1, 2, and 3 samples. But if we look at amphibole, we can see a really stark difference between these three groups. So I've included the bulk rock signatures on the left for comparison, and the amphibole here on the right. It's group 1, again, these flat rare earth element patterns, likewise amphibole. Group 2, light rare earth enrichment, likewise in the amphibole. And then in the group 3 samples, a more pronounced, expanded enrichment in the light and some of the middle rare earths that is reflected by the amphibole. A similar phenomenon is seen in the clinopyroxene chemistry. It's not quite as pronounced, but it certainly exists. So again, flat in the group 1, some mild light rare earth enrichment in group 2, more pronounced in group 3. And also, if we take a look at the chemistry of the calcites that I mentioned, those carbonate minerals, what we can see is, remember, they don't exist in the group 1 samples. In the group 2 samples, we have a restricted enrichment in some of the light rare earth elements. Group 3, a more pronounced enrichment in the light rare earth elements. So what that seems to us then is that there seems to be a mineral chemical control on the geochemistry of these three groups. Hypothesis that we had seems to be controlled by the composition of both amphibole and clinopyroxene. In order to test that, what we did was do some mass balance calculations. So can we recreate the bulk rock pattern that we have analyzed using the composition of amphibole and clinopyroxene and the modal mineral abundances? In the closed symbols is the analyzed composition, and in the open symbols is the calculated composition. And what you can see for all three of these groups that we tested, there is a pretty good replication on these mass balance calculations. So group 1, again, flat trace element patterns. Group 2, negative niobium tantalum anomalies. Group 3, negative niobium tantalum, zirconium, hafnium, and titanium anomalies. Yes. Okay, so what then is controlling this? Let's try and think about this from a petrological point of view. What is causing the high field strength element anomalies, or more specifically, what is causing this light rare earth enrichment in some samples? I'm not going to go through the pros and cons of each hypothesis here. If you are interested in this stuff, I would point you towards this paper that we published in 2018 that I hope gives a reasonably fair hearing to each of the different hypotheses. What I'm going to do here is really talk about the crux of the issue. So are we looking here at primary magmatic processes, or are we looking at secondary processes that has caused these distinctions in the trace element geochemistry? Did the Benstrom complex look like this after it crystallized at 2.85 billion years ago, or is some process between then and now responsible? So one way we might want to test the primary hypothesis is to look at element mobility, try and assess whether elements have moved around after their crystallization. One way in which we might do that would be to use some simple bivariate plots. So on the x-axis, we would include elements that we typically consider to be the most immobile, something like yttrium, zirconium, ytterbium. And then on the y-axis, we would include an element whose mobility we would like to test relative to that on the x-axis. I should say, before explaining this figure, that in order for this method to work, the samples need to be coeval. So in this particular instance, we believe that all of these samples crystallized as part of a layered intrusion. So that would mean that these samples are coeval and that we can use this particular method. So let's start by plotting up all of our Benstrom samples, terbium versus lutetium. What you can see is a really nice positive correlation. It's what you would expect. These elements sit next to each other on the periodic table. Chemically, they behave very similarly. So it would suggest to us that relative to ytterbium, lutetium has not experienced any or much mobility in all of these rocks. If we take a look now then at ytterbium versus gadolinium. Gadolinium is a middle rare earth. It's located here on the trace element plots. You can see it's enriched in some of these samples. We have a reasonable correlation between these group 1 and these group 2 samples, but that correlation is not consistent for the group 3 samples, suggesting to us that gadolinium has been mobilized relative to ytterbium in these rocks. Now, if we then take a look at ytterbium and lanthanum, lanthanum being one of those key light rare earth elements that I've been discussing, located here on the trace element plots and very fundamental for these high field strength element anomalies. What you can see is there is no correlation between ytterbium and lanthanum, suggesting to us that there has been significant mobility of lanthanum relative to ytterbium. Now, if we take out the group 2 and the group 3 samples, leaving only this group, there is a significantly improved correlation between these two elements. You can see the R-squared value is not super high, but there is some semblance of a correlation that didn't exist before. So while there may have been mobility of lanthanum relative to ytterbium in these rocks, there has been significantly less than in the other rocks. So we would argue, based both on this and several other lines of evidence that we include in the paper, that it's unlikely that we can explain this by primary magmatic processes. That leaves us then with something secondary. I should say before I discuss these potential processes, I'm certainly not wedded to the hypothesis that we put forward in the paper. And I would be very keen to hear from people here in the audience, ideas, different ways of approaching this question about how we could try and assess what may have caused this. So yeah, I'm very open to suggestions, open to hearing what people think. So there's a couple of possibilities that I want to outline for you then, in terms of what process may have caused this light rare earth enrichment. The first would be metasomatism associated with felsic partial melts. Now, this was actually proposed by Hugh Rollinson and Philip Gravestock back in 2012. They described similar features to those which we have described here at a locality that is probably 20 or 30 kilometers from the locality that I've described. And they suggested that these felsic partial melts derived from partial melting of the TTG that forms the majority of this Lewisian gneiss complex, carried with it some light rare earth elements, and that interacted with certain samples, generating the light rare earth enrichment. We know that these exist both in the Lewisian and also in the area immediately surrounding the Benstrom complex. I've seen these in and around the Benstrom complex. However, when you look at their chemistry, they're not actually that rich in the light rare earth elements. In fact, some of these rocks have greater abundances of light rare earth elements than the felsic partial melts themselves. So it made us kind of question this hypothesis. And also, I've not seen, it doesn't mean it doesn't exist, doesn't mean it's not there, but I have never seen this kind of thing cross-cutting the ultramafic rocks in the field. So then we thought, well, maybe we need to try and propose something different. And what we decided seemed most likely, based on the evidence that we have here, is that you have metasomatism associated with some H2O, CO2-rich fluids. What's the evidence for that? We would point towards the presence of these carbonate minerals, these calcite veins that exist in some of these group 2 and group 3 samples, which we don't see in the group 1 and the group 2 samples. And we would also point to the composition of these, which show this really distinctive enrichment in the light rare earth elements, both in the group 2 and the group 3 samples. I should say, actually, I forgot to mention when I initially described these data, that these are mixed analyses. So sometimes the carbonate minerals that we were analyzing were smaller than the laser, which meant that we ablated a small amount of silicate material as well. So if anything, this signal that we're looking at is a little bit diluted. So how might then that fit into that complicated polyphase protracted metamorphic history that I described to you at the start? There are lots of possibilities, and as I say, I'm not wedded to the hypothesis we've put forward. We would suggest probably that most likely associated with this later event. You can see that the veins themselves seem to cross-cut everything else. So they cross-cut other metamorphic minerals, other alteration minerals like amphibole and serpentine. So it must be pretty late in the history of these rocks. Again, just to reiterate, if people are interested, head towards this paper. It will give you, hopefully, a more thorough investigation into each of these different hypotheses.
So why would these fluids be enriched?
So, I mean, an obvious sink for this is the majority of this crust in this region is composed of these TTGs, which, relative to the ultramafic rocks, are really abundant in light rare earth elements. So you wouldn't need to mobilize too much, and these are relatively depleted in all of the trace elements. So you wouldn't actually need a process that was too efficient. You just dump a little bit of trace elements, light rare earth elements, and you would end up with this. So. I don't think they have rutile in them, to my knowledge.
Why aren't you affecting the
Well, we would suggest that the light rare earths are more mobile than the high field strength elements. Okay, so it would be easier to mobilize them than to mobilize. You're not mobilizing all elements equally here, and so that would dump just the light rare earths, which are more easily mobilized than other elements. That would be the idea. You're selectively mobilizing certain elements. Does anyone want to ask any questions while we're on the topic? Okay. Okay, so let's try and bring this full circle then back to this question that I asked right at the start of the talk. Are these high field strength elements a good proxy for Archaean subduction? Now, in this particular case, and I emphasize that this is one example from one location, these anomalies seem to have likely been generated by secondary processes. We would therefore argue that these anomalies on their own are a poor proxy for Archaean subduction without some rigorous tests of element mobility and the complicated history that these rocks often record. So just to emphasize this point a little bit, I kind of take you to an alternative universe where I didn't have the luxury that I did have of spending lots of time in the field, spending 6-7 weeks at a time in the field, mapping this thing in great detail. the ability to take lots of samples back and analyze them, access to the analytical equipment that I did. Alternative universe where I'd had 2 weeks to collect all of my samples, let's say, for my PhD, if I was working in a remote location or a difficult to access location. What I might have done is I might have taken 5 samples from the Ben Strome complex, and they might have all looked like this. And I might be stood here today telling you that we've got evidence for 2.85 billion-year-old subduction in the Lewisium. And the key thing here is to emphasize is that it was really tricky to pick this apart, this story. And because these rocks have been subject to multiple phases of metamorphism, so you have multiple phases of amphibolitization, how do you know which of these alteration episodes is carrying the light rare earths? Some probably aren't carrying any of the light rare earths, but the one might not, or that one might be generating a different pattern. So that's the important kind of takeaway here. And while I'm certainly not going to stand here and say that subduction wasn't possible during the Archaean, I'm not prepared to make that sort of a wild claim, but it does pose the question, if this kind of process has gone undetected in rocks, in different cratons, in different parts of the world, and potentially then we've suggested, hey, maybe this is subduction in the Archaean, maybe we're overestimating. Maybe if there's 5 examples of this or 10 examples of this, we're overestimating the role of subduction during the Archaean as a geodynamic process. Food for thought. And just to kind of think again more broadly about our use of these plots. So I mentioned earlier that we order these according to compatibility. What we don't do on these plots is think about the relative mobilities of these elements, of elements that sit next to one another, particularly when these patterns are so important. So, for example, barium is more easily mobilized than thorium, which it sits next to. Lanthanum, as we've shown, seems to be more easily mobilized than tantalum. So these patterns might reflect a metasomatic history that is superimposed upon a primary magmatic history, and something for us to think about. So again, to emphasize that point, I've presented 2 hypothetical scenarios here. So scenario 1 is very much based on what I've just been describing to you, where we've mobilized a lot of elements that typically we wouldn't expect to be mobilized. And I should say, we've got the same starting point in both of these examples. So the closed symbols are our hypothetical starting point. Scenario 1, we have this really spiky pattern with the supposed negative high field strength elements. Scenario 2, we mobilize a more restricted suite of elements during these metamorphic and metasomatic processes, and the pattern looks very different. So, and this kind of dichotomy can be seen on multiple scales. So I've shown it here on a really local scale. I mean, one sample right next to another, the width of your arms. But it can also occur on an inter- and intra-craton basis. So if we're comparing rocks from the Lewisian gneiss complex with another part of the North Atlantic craton, perhaps in Greenland, then we may have different metasomatic histories mobilizing different elements. And the same, of course, can be said for comparing rocks from Greenland with rocks from North America, Brazil, China, South Africa, wherever. So this difference is extremely difficult to unpick and may be important for us, those of us who think about these problems. So just before I summarize what I've been saying, I just wanted to make it clear, I'm stood here presenting this to you today, but it's the work of many people. Very fortunate to have worked with a wide variety of really great scientists and great people who have all brought something different to the party. And in particular, I'd like to just acknowledge Ian and Hannah, who were my PhD supervisors, my primary PhD supervisors. And they have somewhat remarkably, I think, managed to mold me into something approaching a scientist, and I'm very grateful for everything that they've done. So thanks to them. Then just to wrap up what I've been saying, so these negative high field strength element anomalies, it seems to us that you can also generate them by secondary processes. How common this is, I don't know. In this case of the Ben-Ström complex, it seems that it's associated with light rare earth enrichment during metasomatism. We can have a discussion about what specific process might have caused that. And as a consequence, if we're going to invoke Archaean subduction-related interpretations based on these anomalies, we need to be careful. We need to have a good constraint on element mobility. And perhaps we've overestimated Archaean subduction as a consequence. So thank you very much for listening and having me. I really appreciate it, and I'll be happy to take questions now or for the rest of the day. Thank you.
Any questions?
Well, so subduction, the way that convergent margin rocks develop high field strength element anomalies is in essence a metasomatic process.
Mm-hmm.
Because the traditional wisdom is that because of the fluids that are in slab. Metasomatism happens. Ultramafic rocks is not at all uncommon, the carbonatite metasomatism of to investigate convergent margin activity.
Sure.
They use TTG.
Yeah, sure.
The process that you're describing will do exactly what you showed for the ultramafic rock. Not affect the TTG.
Sure. Yeah, yeah. Yeah, I mean, I agree with that. Yeah, the key thing, I mean, the TTG high field strength element anomalies, like you say, chicken and egg. I don't want to wade in too much to that. This is more focusing on these mafic and ultramafic units that we get and trying to understand their origin and their role to play in the cratonization, effectively.
My eyes aren't great these days, but it looked like the rubidium was not nearly
Yes, I will have included.
not as mobile as surprising. Normally considered a very water friendly.
Yeah, I wonder with the rubidium whether we're superimposing different metasomatic events. If you, like you say, rubidium is more easily mobilized. So what we're not looking at here is one simple event. If the rubidium has been maybe taken out, put in, at different stages, and the light rare earths are only associated with one of these events. So yeah, it's difficult to unpick these different events. So I'm trying to think of it like that rather than one event. But like you say, if it was one event, that'd be extremely strange. So we must have superimposed multiple events, I would assume here.
So the other thing is, how do you recognize metasomatism versus some sort of uranium and thorium can be used? The uranium and thorium is less mobile.
Yeah, that does seem to be the case. So yeah, it was just striking to us, yeah, exactly as you described, that it was just this kind of narrow suite of elements that were so enriched when we initially started questioning, what the origin of these data would be. Yeah, absolutely.
I have a question.
Mm-hmm.
You didn't discuss the major elements at all, these rocks.
No.
And I know some of them are going to be mobilized, but they might also lead you to processes going on, like assimilation, standard igneous assimilation of something, maybe not as deep, but something. How do you rule out
Yeah.
that process?
Yeah, so that's one of the hypotheses we mention in the paper, and we have a go at seeing whether it's likely. It didn't seem to us to be likely. I don't think silica didn't correlate with lanthanum at all. So we did some simple mixing calculations between our base ultramafic rocks and the TTG that is in the local area, and you needed something like 50 or 60% TTG input to get to anything that would even approach this. And by that point, it's not an ultramafic rock anymore. It's too silica rich. So yeah, it seemed unlikely based on that, but certainly possible in other scenarios for sure.
While people are thinking, so you've got this very contrasting metamorphic grades between granulite and samples are from the granulite grade terrain, side of the granulite
Yep.
grade terrain. Could you pick similar looking rocks, that you think might have a similar kind of check the amphibole facies terrain? Higher temperature, deeper.
Yeah, the problem is that the ultramafic and mafic rocks are strangely absent from these amphibolite facies regions. So yeah, this is a whole talk to itself, the origin of these things. But we have these kind of pods, this kind of size of mafic rocks throughout all of the regions. But the large scale ones with the beautiful layered ultramafic rocks, they only seem to exist in this central region. So yeah, it's difficult for us to compare. Yeah, for sure.
Anybody else? Any other questions? There's a little time on George's schedule.
Yeah, I can't remember.
Me to get on George's schedule, and let's thank George again. Thank you very much.
Thanks for having me. Thank you.